As we begin our study of the derivative and how to work with derivatives and all of that, which is one of the cornerstones of Calculus 1, we first need to talk about the slope of a tangent line at a point. There are essentially two equations with which we can do this. We'll derive them both, but I want to look at them first to essentially cut to the chase and see where we're going, and then we'll step back and derive each of these, and then we'll learn how to use them to find the equation of what we call the tangent line. The first equation for the slope of a tangent line, which we write as m sub tan, that m is our standard slope m. So we have that equal to the limit as x goes to a of f of x minus f of a all over x minus a. You may recognize that as the difference quotient, that f of x minus f of a all over x minus a. And that's why we spent so much time studying the difference quotient, is because now we use it to find the slope of the tangent line. The second version of slope of a tangent line that we'll study is m sub tan equals the limit as h goes to 0 of f of x plus h minus f of x all over h. So one's not necessarily better than the other when it comes to these. Sometimes one is more useful than the other. So we'll derive them both, and then I'll show you how to use them to find the equation of a tangent line. Let's start with the x minus a version of the slope of the tangent line. So you take some function, essentially like this, some f of x. What we're interested in is the slope of this curve at a single point on the curve itself. So we want the slope just at a point. Usually a slope takes 2 points to determine, but we want to be able to determine the slope just at one point. So in this example, at this point, we'll call it a here. So if we go down to the x-axis, we have a. So we'll call it a comma f of a for the y value there. And the slope just at that point, a comma f of a, might look something like this. Right? It just comes up and touches the line at that one point, and you can imagine it matching the slope. If we could determine just the slope of that curve at a single point, it would be about the same as the slope of that blue line there. And we can do this for any point, right? Take another point somewhere up here, maybe on the function. Okay, well, we can determine the slope at that point. Maybe it looks something like that. These blue lines here are called tangent lines. The tangent lines essentially come through and just touch the function right at the point of interest and give us an exact slope at that point. Now, how do we arrive at these mathematically? To arrive at the equation of a tangent line at the point A, we essentially start with some point x away from A and draw a line through the 2 points. So here's some point x away from A. We'll label that as x comma f of x. And we can connect these 2 points to find the slope of what's known as the secant line. And then we can talk about the slope of the secant line. So we write that as m sub sec for secant. Okay, well that's just the same thing as any line, rise over run. Okay, so then remember the equation for the slope of a line is something like this: y2 minus y1 over x2 minus x1. That's just the rise over run equation. So let's call a f of a x1 y1, so x1 and y1, and let's call f and f of x x2 and y2. Okay, so then using this equation for slope, we get f of x minus f of a all over x minus a. So that gives us the slope of the secant line, which is also known as the average rate of change. What we want is the instantaneous rate of change, which is the slope of the tangent line at exactly the point A, comma f of a. So what we'll do here to obtain that is we'll take our x and move it in towards A using a limit. That takes this point and moves it down the curve ever and ever closer to A until we're actually on only the point A itself. So the second point is getting closer and closer and closer until there's only one point. Once there's only one point, we no longer talk about the secant line, we talk about the tangent line. Well, how do we move something closer and closer and closer? We have a tool for that. It's the limit. So then we say that the slope of the tangent line, which is what we've been looking for, is the limit as x goes to A of the slope of that tangent line. So f of x minus f of a all over x minus a. And that gives us the instantaneous rate of change, which is what we're interested in calculus. Average rate of change, that was more of a pre-calculus thing. Now let's go back and derive the h version of the formula of the slope of the tangent line. Okay, so we have the same function with the same secant line, but we'll derive a different formulation for the slope of a tangent line. So we have the slope of the tangent line is the limit as h goes to 0 of f of a plus h minus f of a all over h. And you'll see both formulations of the slope of the tangent line in different textbooks. I would say this h version is used slightly more often. I find it just a little easier to work with because we just have the single variable in the denominator there to worry about. Now, you may have noticed earlier in this video I put up a formula that said x here, f of x plus h minus f of x. That was a slight mistake. The main formula that we use is x. It's weird to have an a here. In this section, we're introducing the formula for a single point a, and then we'll go back and redo this whole thing for a general point x. So it's tempting to just slip back into x mode, but right now we're doing it just for a. So let's look at this for a single point a. Now, if you're looking at the graph, you may notice that there's not an h anywhere on here. So where is this h coming from? Well, it comes from the fact that instead of this x here for the second point, so I'm going to erase everything to do with this x for a second point, and I'm going to reformulate this as, so we start with our a, and then we're going to go a distance h to the second point. So I'm going to label this distance as h. What does that make the second point? It makes that second point a plus h. So then up here, if we actually look at so a plus h on the x-axis, the point itself is a plus h for the x value, and then f of a plus h for the y value. Okay, so there's our ordered pair. We still have our same secant line, so let's do our slope of the secant line, just as we did before. Slope of the secant line is, okay, rise over run, so we'll do y2 minus y1, exactly the same thing we did before, over x2 minus x1. Okay, so let's write this as f of a plus h minus f of a all over a plus h minus a. And of course, notice that the a's cancel out in the denominator, giving us exactly what we need. F of a plus h minus f of a all over h. So that's the secant line. And then what we do to get the tangent line at the point, which is what we're interested in again in calculus, is we're going to take this second point, this a plus h, and slowly or quickly, I guess, move it to all the way down to this a. Well, what do we do mechanically to make that happen? We shrink this h down to 0. As h goes to 0, this a plus h point is going to go back and back towards a, and eventually we'll get the slope right at this point, a comma f of a, which will give us the slope of the tangent line instead of the secant line, because we'll only have one point. Well, how do we let something get closer and closer and closer? We take the limit. So let's see here. So we have the slope of the tangent line then is the limit. So the limit's really good for, as h now goes to 0, we're shrinking that h down to 0 of f of a plus h minus f of a all over h. Okay, that's a lot of theory. Let's bring this down to earth a little bit with a solid example. Find the equation of the line tangent to f of x equals 8 minus 2x squared at the point 0, 8. Well, we're looking for a line here. So let's start with the equation of a line. So you'll recall from pre-calc or somewhere like that, the point slope form of a line, which is y minus y1 equals m times the quantity x minus x1. And remember that x1, y1 are actual physical points, and then you leave x and y as variables. So luckily we're given a point here. Look at this. So 0 is our x1, 8 is our y1. And then we'll leave x and y as they are. M, that's going to be m tangent here. And luckily we have a formula for m tangent. In fact, we have two of them. We can choose our favorite. My personal favorite is the H version, so I'm going to go with that one. Feel free to use either one, but I kind of recommend focusing more on the H version. It's just a little more useful. So here's the slope of our tangent line. The limit as h goes to 0 of f of a plus h minus f of a all over h. Well, what's a in this case? So pause the video if you need to think about that for just a second here. Can you determine what a is in this example? Well, a is the x value in this case, or in all cases. So it's always the x value here. So this 0 is our a, as well as our x1. So we can do this calculation. So we'll have m tan, the slope of the tangent line is the limit, okay, as h goes to 0. Since h is going to 0, we want to get this h to cancel out. All right, so that's what we need to focus on in these kinds of examples. It's the same thing we needed to focus on for the difference quotient back in earlier in this course and in pre-calculus. Okay, so let's see if we can get that h to cancel out. We have f of a plus h, but a is 0, so we have 8 minus 2 times 0 plus h quantity squared. Okay, there's f of a plus h minus, now we'll do f of 0. So minus, I'm going to put the whole thing in parentheses here, 8 minus 2 times 0 squared all over h. Okay, so let's just slow this down, make sure we're on the same page here. This is f of 0 plus h. The second one here is f of 0 all over h. Okay, moving forward, we have the limit as h goes to 0. Well, let's see here. 8 minus 2h squared minus 8. Well, then the second term in here goes to 0 anyway. So that's all we have up top, all over h. And look at this. This is where we get our h in the denominator to cancel out. We have the limit as h goes to 0. 8 minus 8, those cancel out. So we have minus 2, and then we have h squared over h, which just leaves us with minus 2h. Now we can evaluate the limit. The limit as h goes to 0 of this is indeed just 0. So interesting. So the slope of our tangent line is 0. Okay, we don't stop here because what we actually want out of this exercise is the equation of a line. So we'll start with the point-slope form, though you always represent your answers in the slope-intercept form of line, y equals mx plus b form. But the point-slope form is more useful to get there. Okay, so let's do that. So we have y minus y1. We decided y1 was 8 equals m tangent. We decided that was 0. X minus x1. We decided that was 0. So all of this on the right-hand side goes to 0. So that leaves us with y equals 8 for our tangent line. Well, what kind of line is that? Think to yourself, can you imagine what this line looks like? Indeed, it's a horizontal line that goes to the point y equals 8. So let's jump over to Desmos and visualize this function along with the tangent line to see if we can make sense of all this. Okay, here we are in Desmos. We have in red 8 minus 2x squared, and then we can see the tangent line here in blue. And it makes sense because the tangent's hitting right where this function turns around. So if we could imagine just at that single point at the top of the parabola there, the tangent line would indeed be horizontal, which is exactly what we have, a horizontal line right where this thing turns around. It turns out that exact idea will be very important in calculus because we want to know where a function goes up and turns around, because what does that give us? It gives us the maximum. And finding the maximum of something is very important, right? Just imagine maximizing profit or energy output. The same thing for minimum. Maybe we want to minimize waste or the distance a truck goes for a delivery, right? So when you can maximize or minimize something, it's of huge interest for us in calculus. And so we can see just a little taste of that here. The maximum point on this parabola corresponds to a horizontal tangent line.